68 million years ago, give or take a few 100,000, in a part of the world we would eventually call Montana, the air was warm and heavy with moisture. Ferns taller than a grown man lined the banks of a slow, winding river. Conifers and flowering magnolias rose above them, their canopy filtering the late afternoon sunlight into shafts of gold and green. Insects hummed in dense clouds above the water. A turtle the size of a coffee table hauled itself onto a sandbar and settled into the warmth. Somewhere nearby, a small furry creature no bigger than a rat watched from its burrow, waiting for night. And then the ground began to vibrate. Not an earthquake, not a tremor. Something rhythmic, something alive. A low-frequency pulse that you would feel in your ribs before you heard it, and travelling through the wet earth like a drumbeat, steady and patient and impossibly heavy. The turtle froze. The small mammal retreated deeper into its hole. Even the insects seemed to pause, as though the forest itself had drawn a breath and was holding it. 12 meters away, a shape moved between the trees. What you would have noticed first, if you had been standing there, was not the size, not the teeth, not the tiny arms or the massive skull. What you would have noticed first was the sound, or rather the absence of it. The forest, which a moment ago had been alive with birdsong and insect hum and the gentle splash of fish in the shallows, had gone completely silent. That is what happens when an apex predator moves through its territory. The entire ecosystem holds its breath. Every animal that can hear, and many that rely on vibration rather than sound, go still. The frogs stop calling, the birds stop singing. The insects that have been droning in the humid air for hours go quiet, as though someone had turned down the volume on the world. Then you would have felt the footfalls, not heard. Felt. Each step landing with the careful, deliberate precision of something that weighs as much as a delivery truck, but moves with a grace that seems impossible for an animal of its size. The ground transmitted each impact as a low, subtle pulse, almost below the threshold of human perception, a vibration that travelled through the soil and the water and the roots of the ferns and registered in some deep, instinctive part of your brain that understands, without needing to be told, that something very large and very dangerous is very close. And then you would have seen it, emerging from the shadows between two massive conifers, its body held horizontally, its tail extended behind it as a counterbalance, its head turning slowly from side to side with the smooth, mechanical precision of a surveillance camera. The skin, covered in a texture somewhere between scales and the remnants of filamentous feathers, was mottled in patterns that broke up its outline against the dappled forest light. Not bright, not dramatic, just effective. Camouflage designed not for beauty, but for the single purpose of making 9 tons of predator marginally harder to see until it was too late. The eyes were what would have held you, set forward in the skull, large and dark and watchful. They tracked across the environment with an attentiveness that you would recognize instantly, because you have seen it before. You have seen it in the eyes of hawks perched on highway signs, scanning the grass below. You have seen it in the eyes of cats watching birds through a window, every muscle still, every sense focused. That look, the look of something that is paying attention to everything simultaneously and is deciding moment by moment what to do about it. This was Tyrannosaurus rex, not the museum skeleton with its empty eye sockets and its wired-together jaw, not the CGI creation leaping over fences and chasing helicopters, the living animal, the real thing. And tonight, we are going to understand it in a way that no movie, no documentary and no museum exhibit has ever quite captured. You have seen Tyrannosaurus rex before. Of course you have. You have seen it roaring on movie screens, assembled in museum halls, imprinted on the children's backpacks and plastic lunchboxes. You have seen it rendered in CGI, sculpted in bronze, painted in oil, stamped on postage. It is arguably the most famous animal that has ever existed, more recognizable than any living species, more deeply embedded in our collective imagination than the lion or the eagle or the whale. You know what it looks like. You know the silhouette, the tiny arms, the enormous head, the rows of teeth. You have known these things since you were a child, but here is something that might surprise you. Almost everything the popular imagination gets right about this animal is a simplification, and almost everything it gets wrong is more interesting than the fiction. Tonight we are going to take Tyrannosaurus Rex apart, piece by piece, and look at what was actually there. Not the monster from the movies, not the cartoon villain of 1,000 documentaries, the real animal. The one that science has spent more than a century studying, and is still, as of this year, discovering new things about. Because nothing about T-Rex was normal, not its eyes, not its nose, not its bite, not its arms, not the way it grew, or the world it lived in, or the sheer number of them that walked the earth over the millions of years they existed. Every aspect of this animal, when you look at it closely, turns out to be more extreme, more sophisticated and more strange than you were ever taught. So settle in. Dim the lights if you haven't already. Let the modern world fade away for a while, and let me take you back to the late Cretaceous, and to a time when the most extraordinary predator in the history of the terrestrial life was not a legend or a fossil or a toy. It was alive. It was breathing. And it was looking at the world through eyes that could see things no living animal can see today. There is something else about the world of 68 million years ago that is worth understanding before we go further, because it shapes everything that follows. The climate of the late Cretaceous was, by modern standards, extraordinarily warm and stable. The global average temperature was significantly higher than today, and the seasonal extremes that define modern temperate life simply did not exist. The Earth had been in this greenhouse state for over 150 million years, from the beginning of the Jurassic through the end of the Cretaceous. The dinosaurs had evolved in this warmth, but it was the only climate they had ever known. This matters because it tells us something about the metabolic environment in which T-Rex operated. A warm, stable climate means abundant vegetation, which means abundant herbivores, which means abundant food for a predator at the apex of the food chain. T-Rex did not live on the edge of starvation. It lived in a world of plenty, a world where the challenge was not finding food, but securing it against competition, and processing it efficiently enough to fuel a body that consumed enormous amounts of energy every single day. Let's start with what T-Rex actually looked like, because the image in your head is almost certainly wrong. The first thing you need to let go of is the tail dragger, the upright, Godzilla-like posture with the tail dragging on the ground behind it, with the body held nearly vertical, the head jutting forward like a man in a suit. That reconstruction dominated museums and textbooks for most of the 20th century, and it was based on a fundamental misunderstanding of how theropod dinosaurs held themselves. Modern biomechanical analysis has shown that T-Rex carried its body in a horizontal posture, balanced like a massive seesaw, with the heavy skull counterweighted by the long muscular tail held straight out behind. The spine was roughly parallel to the ground. The legs were directly beneath the hips, bearing the full weight of an animal that could tip the scales at anywhere between 5.5 and nearly 9 tons, depending on the individual and its age. The weight range alone should give you pause. 5.5 to 9 tons, the most complete T-Rex specimen ever found, a skeleton known to paleontologists by its catalogue number, but known to the rest of us by a name, measures between 12.3 and 12.4 meters from snout to tail tip. That is roughly 40 feet, longer than a city bus. The skull alone, in the largest known specimens, measured up to 1.52 meters, which is 5 feet from the tip of the snout to the back of the cranium. Imagine a skull you could barely wrap your arms around, a skull with openings large enough to reduce its weight, because without those openings it would have been too heavy, even for T-Rex's massively muscled neck to support. And here is something else the popular image misses. T-Rex was not alone. For decades, paleontologists debated whether a set of smaller tyrannosaur fossils found in the same geological formations as T-Rex represented juvenile specimens of the same species. essentially teenage T. rexes that hadn't finished growing, or a completely separate animal called Nanotyrannus. The debate raged for years with respected scientists on both sides. Then in 2025, a study published in the journal Nature settled the question. The evidence came from one of the most spectacular fossil discoveries in paleontological history, a specimen known informally as the dueling dinosaurs. Found in Montana, it preserves two animals locked in what appears to be prehistoric combat. A triceratops and a smaller-bodied tyrannosaur, their skeletons intertwined as if frozen in the act of killing each other. The fossil was acquired by the North Carolina Museum of Natural Sciences, and when paleontologists Lindsay Zano and James Napoli finally published their analysis, the result was unambiguous, and the smaller tyrannosaur was not a juvenile T-Rex. It was an adult Nanotyrannus, a completely separate genus with its own distinct anatomy. Long arms with a vestigial third finger, narrower jaws, longer legs relative to its body, and bone microstructure that proved beyond doubt it had reached maturity. As Napoli put it, for Nanotyrannus to be a juvenile T-Rex, it would need to defy everything we know about vertebrate growth. It was not just unlikely, it was impossible. This discovery didn't just settle a decades-old argument. It rewrote the story of T-Rex's world. For years, scientists had been using Nanotyrannus fossils to model T-Rex growth and behaviour, building theories about how the Tyrant King developed from juvenile to adult. Those theories were based on two entirely different animals, and the ecosystem of the final million years of the Cretaceous was richer and more competitive than anyone had realised, with multiple tyrannosaur species coexisting in the same environment. Zano and Napoli even identified a second species of Nanotyrannus from the same deposits, which they named Nanotyrannus lithius, after the river Lethe from Greek mythology, a nod to how this species had been hidden in plain sight and forgotten for decades. So the landscape of late Cretaceous North America was not a kingdom ruled by a single species of tyrant. It was an ecosystem with layers of predators, each adapted to different prey, different hunting strategies, different niches. T-Rex was the undisputed apex, the largest and most powerful, but it shared its world with smaller, faster relatives that had their own roles to play. This is the real T, a Rex. Not a solitary monster stomping through a barren landscape, but the apex of a complex, layered, astonishingly diverse ecosystem, an animal whose every feature, from its eyes to its toes, tells a story of millions of years of evolutionary refinement. An animal that, even after more than a century of study, continues to surprise the scientists who dedicate their careers to understanding it. Before we go any further, if you are enjoying this, consider subscribing. I put these together because I find this genuinely fascinating, and I suspect you do too. There is so much more to cover tonight, and it only gets stranger from here. Now, let's talk about the eyes. There is a scene in the original Jurassic Park, the 1993 film, that burned itself into the memory of an entire generation. The T-Rex has broken loose from its enclosure. It is standing in the rain, enormous and terrifying, just a few feet from the characters played by Sam Neill and the two children. And Sam Neill's character, Dr. Alan Grant, whispers something that became one of the most quoted lines in movie history. Don't move. It can't see us if we don't move. It is a brilliant piece of cinema. It is also, as a piece of paleontology, completely wrong. A scientist named Kent Stevens at the University of Oregon was so bothered by that scene that it inspired him to spend years investigating what T-Rex could actually see. Stevens was a vision researcher by training, and he recognized that the tools used in human ophthalmology, specifically a technique called perimetry, which maps the extent and quality of a patient's visual field, could be adapted to study extinct animals. He built sculpted, life-sized reconstructions of the heads of 7 theropod dinosaur species, including T-Rex, and using a novel approach he called inverse perimetry, involving taxidermic eyes, a laser, and a glass plate, he mapped their binocular fields of view. The results, published in 2006 in the Journal of Vertebrate Paleontology, were startling. T. rex had a binocular range of 55 degrees. To put that number in context, a modern hawk, the bird most celebrated for its sharp vision, has a binocular range narrower than that. The forward-facing eyes of a red-tailed hawk, the raptor that circles above open fields, scanning for mice from hundreds of feet in the air, provides it with less visual overlap than T. rex had. Every predatory bird that you have ever watched dive for prey, every eagle and falcon and osprey, and I was looking at the world through a narrower window of three-dimensional vision than the 12-meter carnivore that walked the Hell Creek floodplains 68 million years ago. And it gets more remarkable from there. Stevens didn't stop at binocular range. He also studied the visual acuity of T. rex, meaning how sharply it could resolve detail at a distance, and he did this by examining the eyes of T. rex's closest living relatives, animals that share its basic eye architecture. He looked at alligators, which have eyes adapted for night vision. He looked at ostriches, which have a mix of night and daytime capability, and he looked at eagles, which have eyes adapted for extreme daytime sharpness. Using these as a bracket, a range of possible performance levels, he estimated where T. rex's vision likely fell, and the best case estimate was extraordinary. T. rex may have had visual acuity up to 13 times greater than a human being. 13 times. An eagle, for all its legendary sharpness of sight, has visual acuity about 3.6 times that of a person. If Stevens's upper estimate is even close to correct, T. rex could see fine detail at distances where you and I would see only a blur. Even toward the cautious end of his estimates, even accounting for every uncertainty, T. rex still had significantly better vision than what would be needed for scavenging, than what would be needed for spotting stationary prey, than what would be needed for anything other than the precision tracking of living, moving targets across enormous distances. Stevens also estimated what he called a limiting far point, the greatest distance at which an object remains distinct from the background, separate from the horizon, resolvable as a thing unto itself. For T. rex, that distance may have been as far as 6 kilometers, nearly 4 miles. Think about what that means. If you were standing on an open floodplain in the late Cretaceous, a T. rex 6 kilometers away could potentially see you, not as a vague shape, not as a smudge on the horizon, as a distinct identifiable object, something worth investigating, something worth walking toward. The anatomical basis for this extraordinary vision is written into the skull itself. T. rex's eyes were large, roughly the size of a softball, set into a cranium that was extremely wide at the rear but narrow at the snout. This skull geometry is the key. In most large theropod dinosaurs, like Allosaurus or Carcharodontosaurus, the snout was tall and wide, and the eyes were placed more toward the sides of the head. This gave them a wide field of view, useful for detecting emotion on the periphery, but it restricted the overlap between the two eyes, the area where both eyes see the same thing, to only about 20 degrees, comparable to a modern crocodile. Good enough for an ambush predator, not good enough for precision depth perception. T. rex evolved in the opposite direction. Over millions of years, as the tyrannosaur lineage refined itself, the snout grew lower and narrower. Grooves developed in the cheekbones that cleared the sight lines forward. The eyeballs grew larger. The entire front end of the skull was reshaped to maximize the area that both eyes could see simultaneously, and the result was an animal with binocular overlap, comparable to a hawk's in visual acuity that may have exceeded it. This was not an accident of anatomy. This was the product of sustained, directional selection pressure across millions of years. T. rex's skull was sculpted by evolution into a precision optical instrument, and every generation moved it a little further in that direction. A separate study, conducted by Lawrence Whitmer and Ryan Ridgely at Ohio University, reinforced these findings from a different angle. Using CT scans of tyrannosaur brain cases, they found evidence of relatively rapid and coordinated eye and head movements, the kind of neural infrastructure you would expect in an animal that needed to track fast-moving objects in three-dimensional space. And this is not the neurology of a scavenger lumbering toward the smell of a carcass. This is the sensory architecture of an active, visually oriented hunter tracking prey through a complex environment with the kind of precision that modern rhetorial birds use to pluck fish from the surface of a lake at 60 miles per hour. And there is one more detail about T-Rex's eyes that is worth pausing on, because it tells us something about the animal's life that the bones alone cannot reveal. The forward-facing binocular vision that T-Rex evolved is, in every living animal that possesses it, associated with predation. Owls have it, hawks have it, cats have it. In every case, the ability to judge distance with precision, to see in 3 dimensions, to resolve fine detail at a distance, is linked to the pursuit and capture of prey. Herbivores, they almost universally, have their eyes placed on the sides of their heads, maximizing peripheral vision so they can spot approaching danger. Predators have their eyes facing forward, maximizing depth perception so they can judge the exact distance to their target. T-Rex had the most extreme version of forward-facing vision of any large theropod ever discovered. Its skull was literally built around the principle of seeing forward, of seeing in 3 dimensions, of seeing with a clarity and a reach that surpassed the most celebrated visual predators alive today. Every bone in the front half of that skull was arranged to serve the eyes. So the next time you picture Tyrannosaurus rex, don't picture the clumsy, half-blind movie monster fooled by stillness. Picture something closer to the truth, an animal that could see you from 4 miles away, and that could judge your exact distance, your speed, your direction of travel, with the precision of a fighter pilot, that evolved its entire skull to serve a pair of eyes that were, by any measure, among the most finely tuned visual instruments the animal kingdom has ever produced. There is one additional detail about T-Rex's visual system that deserves attention, because it connects the anatomy to the behavior in a way that brings the animal to life. When you watch a hawk hunt, you notice something about the way it moves its head. It doesn't track prey the way a human tracks a moving object, by smoothly panning the eyes from left to right. Instead, it makes rapid, precise head movements, snapping from one fixation point to another, and holding each position just long enough for the visual system to process what it sees before snapping to the next. This is because the hawk's eyes are fixed in their sockets. They cannot swivel the way mammalian eyes do. The entire head must move to redirect the gaze. T-Rex had a similar constraint. Its eyes, while enormous and beautifully positioned for binocular overlap, were likely limited in their ability to rotate within the skull. To track a moving target, T-Rex would have needed to move its entire head, which means it would have needed rapid, precisely controlled neck movements, exactly the kind of neuromuscular coordination that Whitmer and Ridgely found evidence for in their CT scans. Picture it, an animal the size of a bus, its massive skull swiveling with the crisp, mechanical precision of an owl, locking on to targets, assessing distances, calculating approach vectors, all with a visual system that could resolve details at distances that would make an eagle envious. There is something deeply unsettling about that image. We are accustomed to thinking of large animals as slow, lumbering, imprecise. The idea of something that massive tracking you with the head movements of a hunting bird, with that level of focus and precision, is profoundly uncomfortable. And it should be, because that is exactly what T-Rex did, every single day of its long, slow, 40-year journey from hatchling to apex predator. And those eyes were just the beginning. Because while T-Rex was watching the world through the sharpest binocular vision of any large predator in history, it was also doing something else. It was smelling the world, and through a nose that was every bit as extraordinary as its eyes. Most predators in nature specialize. A hawk has incredible vision but a mediocre sense of smell. A wolf has a keen nose but eyes that are, by the standards of a raptor, unremarkable. There are good evolutionary reasons for this. Building and maintaining an advanced sensory system is expensive, metabolically speaking. The brain tissue required to process visual information, the neural wiring for olfactory analysis, the enlarged organs and receptors that make these systems work, all of it costs energy. And energy in the wild is always limited. Most animals invest heavily in one primary sense, the one that matters most for their survival strategy, and let the others develop to a more modest degree. T-Rex apparently didn't get this memo. When paleontologist Chris Brochu performed CT scans on the skull of Sue, the most complete T-Rex skeleton ever discovered, now housed at the Field Museum in Chicago, he found something that changed how scientists understood the animal's brain. The olfactory bulbs, the regions of the brain responsible for processing smell, were enormous. Roughly the size of grapefruits. Previous research had suggested that approximately half of T-Rex's brain volume was devoted to processing smell, a proportion that would be remarkable in any animal, let alone one that also possessed the visual acuity we just discussed. In 2019, a team of researchers from University College Dublin, led by computational biologist Graham Hughes and paleontologist John Finarelli, took this investigation further. They wanted to know not just how big a Rex's olfactory bulbs were, but how many olfactory receptor genes the animal likely possessed. These are the genes that encode the proteins on the surface of nasal tissue that bind with specific odor molecules, each receptor responding to a different smell. The more receptor genes an animal has, the more nuanced and detailed its olfactory world. The problem, of course, is that T-Rex DNA is long gone. It degraded tens of millions of years ago, and no amount of amber-trapped mosquitoes will bring it back. So Hughes and Finarelli did something clever. They built a database linking the olfactory bulb sizes and olfactory receptor gene counts of 42 living bird species, 2 extinct birds and the American alligator. In living animals there is a reliable correlation between the two. Animals with more olfactory receptor genes tend to have proportionally larger olfactory bulbs. By establishing this relationship in species where both measurements are available, the researchers could project backward, using the known olfactory bulb sizes of extinct dinosaurs, preserved as endocasts on the inside of fossilized skulls, to estimate how many receptor genes those animals likely carried. The results, published in Proceedings of the Royal Society B, placed T-Rex at the very top of the chart. The researchers estimated that Tyrannosaurus rex possessed between 620 and 645 genes encoding olfactory receptors. To put that in perspective, that count is only slightly smaller than the number found in modern domestic cats and chickens. Closely related tyrannosaurs like Albertosaurus showed similarly high counts. Among all the dinosaur species examined in the study, the tyrannosaurs had the best estimated sense of smell. Now, think about what a domestic cat can do with its nose. A house cat can detect the presence of another cat that passed through a room hours earlier. It can identify individual humans by scent alone. It can smell food through sealed packaging. And T-Rex had a comparable number of olfactory receptor genes, housed in olfactory bulbs the size of grapefruits, connected to a brain that devoted roughly half its processing power to interpreting what those receptors detected. What could T-Rex smell? We can make educated inferences based on the receptor gene clusters that have been identified in its living relatives. It could almost certainly detect blood, a critical ability for a predator and scavenger alike. It could detect the chemical signatures of vegetation, which might seem irrelevant for a carnivore, until you consider that prey animals spend their lives among plants, and the ability to distinguish prey scent from background vegetation is precisely what separates a functional hunter from a confused one. It could likely detect the pheromones and hormonal signatures of other tyrannosaurs, useful for finding mates, identifying rivals, and establishing territory. Let me give you a concrete image of what this sensory combination would have looked like in practice, because the raw data, the receptor counts and bulb sizes and acuity estimates can sometimes obscure the living reality of the animal. Imagine a late afternoon on the Hell Creek floodplain. A herd of Edmontosaurus, several hundred strong, is moving along the far bank of a braided river system, feeding as they go, their duck-like bills cropping vegetation, with a mechanical efficiency that has kept their species fed for millions of years. They are large animals, 10 to 12 meters long, and they move with the unhurried confidence of creatures that find safety in numbers. The wind is blowing from the west, carrying the warm, organic scent of the herd across the river and out over the floodplain beyond. 3 kilometers away, behind a line of conifers at the edge of a forested rise, a T-Rex lifts its head. It has been resting in the shade, conserving energy during the hottest part of the day, its massive body radiating warmth like a boulder that has been sitting in the sun. But now something has changed. The wind has shifted. I am buried in the complex bouquet of river mud and flowering plants and the faintly sulphurous tang of decomposing vegetation. There is something else. Something warm-blooded and alive and present in large numbers. The olfactory centres of the Tyrannosaur's brain light up. Hundreds of distinct receptor types fire simultaneously, each one responding to a different molecule in the scent profile drifting across the plain. The brain assembles these signals into a coherent picture, the way your visual cortex assembles millions of individual photon detections into an image. The T-Rex doesn't just smell something. It identifies what it smells. Hadrosaur. Multiple individuals. Upwind. Distance. Based on scent concentration and wind speed. Approximately 3 kilometers. The animal rises. It turns its head, and those immense eyes scanning the landscape ahead. Through the trees across the open ground, past the glittering surface of the river, it sees them. Hundreds of large shapes moving along the far bank. At 3 kilometers, a human would see only a dark smudge against the vegetation. The T-Rex sees individuals. It sees the way they are spaced, the direction they are moving, the presence or absence of juveniles on the periphery of the herd. It assesses the situation the way a wolf assesses an elk herd from a ridgeline, not with conscious deliberation, in the way we understand it, but with the rapid, practiced pattern recognition of a predator that has been doing this its entire life. It begins to move. Not quickly, not yet. And there is no need for speed when you can track your target from 3 kilometers away and your target has no idea you exist. This is what it meant to be T-Rex, not a blind, rampaging monster charging through the undergrowth, a patient, calculating, sensory-driven hunter that could detect, identify, and begin stalking its prey from distances that would make a modern wolf envious. Every sense working together, every piece of information cross-referenced and integrated, the eyes confirming what the nose detected, the ears monitoring for changes in the target's behaviour, all of it feeding into a brain that, while not capable of abstract thought, was exquisitely designed for this one task. The researchers were careful to note that their study does not settle the old debate about whether T-Rex was primarily a predator or a scavenger. A powerful sense of smell is useful for both strategies. Wolves track living prey over enormous distances using scent. Turkey vultures find carrion from miles away using the same sense. But when you combine this olfactory power with the visual system we discussed earlier, the answer starts to lean heavily in one direction. Scavengers don't need 13 times human visual acuity. Scavengers don't need binocular depth perception wider than a hawk's. Scavengers don't need rapid, coordinated eye and head movements designed for tracking moving objects. Those are the tools of a hunter. And there was a third sense, one that completed the picture in a way that made T-Rex even more formidable than its eyes and nose alone would suggest. The CT scan research by Lawrence Whitmer and Ryan Ridgely at Ohio University, on which we touched on briefly when discussing vision, revealed something else about the tyrannosaur brain. The inner ear structures, specifically the semicircular canals and cochlea, showed adaptations consistent with an enhanced ability to sense low-frequency sounds. These are the deep, rumbling vibrations that travel enormous distances through air and ground, the kind produced by large animals moving through a landscape, by footfalls and breathing, and the distant crash of a multi-ton herbivore forcing its way through underbrush. Picture the implications. T-Rex could see a potential target from 6 kilometers away in open terrain. It could smell prey from further than that, carried on the wind across the floodplains. And it could hear, or rather feel, the low-frequency vibrations of large animals moving through its territory, a sensory channel that worked through darkness, through dense vegetation, through any condition that might limit sight or scent. This was not a blunt instrument. This was not the dim-witted, overpowered brute of 1,000 cartoons. This was a sensory platform of remarkable sophistication, the product of millions of years of evolutionary refinement, an animal that perceived the world through 3 independent but complementary channels that together provided a level of environmental awareness that has no parallel in any living land predator. A wolf can track you by scent. A hawk can spot you by sight. T-Rex could do both simultaneously, while also detecting your footsteps through the ground. And all of that sensory information, all of those inputs from those acute eyes and that sensitive nose and those sensitive inner ears, all of it was being processed by a brain that, while not large relative to its body size, was highly specialized. The regions devoted to smell, vision, and balance were all disproportionately developed compared to the rest of the brain. This was not an animal with a generalist mind. This was an animal whose brain was purpose-built for hunting, every circuit tuned to the detection, tracking, and interception of prey. There is one more dimension to this sensory picture that deserves mention, because it connects to a question that has fascinated paleontologists for decades. Was T-Rex warm-blooded or cold-blooded? The traditional view, inherited from the era when dinosaurs were classified as reptiles and assumed to share the sluggish metabolisms of modern lizards and snakes, held that T-Rex was ectothermic, or dependent on external heat to maintain its body temperature, slow-moving in the cold weather, energetically conservative, fundamentally different from the warm-blooded mammals and birds that would eventually replace it. That view has been almost entirely overturned. A 2006 study published in PLOS Biology by James Gillooly and colleagues estimated that T-Rex had a body temperature of approximately 33 degrees Celsius, only about 7 or 8 degrees Fahrenheit lower than our own mammalian temperature, but vastly warmer than any modern ectothermic reptile of comparable size. Other researchers have proposed even higher estimates. The consensus that has emerged over the past 2 decades is that T-Rex, like most large dinosaurs, was probably somewhere between the traditional categories, not fully endothermic like a mammal, not fully ectothermic like a lizard, but something in between, what paleontologists call mesothermic or gigantothermic, an animal whose sheer mass allowed it to maintain a stable, warm internal temperature without the metabolic expense of true endothermy. What this means in practical terms is that T-Rex was not a sluggish, cold-blooded reptile waiting for the sun to warm it up each morning. It was an active, metabolically vigorous animal, capable of sustained physical effort, capable of maintaining its sensory systems at full capacity, regardless of the ambient temperature, capable of hunting in the cool hours of dawn and dusk, when a truly cold-blooded predator would have been too sluggish to function. The brain that processed all that sensory information, the muscles that powered those bone-crushing jaws, and the legs that carried 9 tons of predator across the landscape at 15 miles per hour. All of it was fueled by a metabolism that ran warm, steady, and relentless. This is the complete picture. An animal with the vision of a hawk, the nose of a cat, the hearing of an elephant, and the metabolic engine to keep all of those systems running at full capacity, day and night, season after season, for 40 years. But detection and tracking are only part of the equation. Once T-Rex found what it was looking for, it needed to kill it. And for that, it relied on what may be the most terrifying biological weapon in the history of life on land. The teeth of Tyrannosaurus rex have been called killer bananas, and the comparison is more apt than it might seem. Each tooth was up to 18 centimeters long, roughly 7 inches, thick and conical, rather than flat and blade-like, with serrated edges running along both sides like the teeth of a steak knife. Unlike the slicing teeth of an Allosaurus or a Velociraptor, which were designed to cut through flesh in a lateral motion the way a butcher's knife draws across meat, T-Rex teeth were built for a different purpose entirely. They were designed to penetrate, to punch through hide and muscle and, critically, through bone. This distinction matters more than you might think, because it reveals something fundamental about how T-Rex fed and what made it different from every other large predator the world had ever seen. Think about the engineering problem that T-Rex's skull had to solve. It needed to be large enough to house the massive jaw muscles required for a bone-crushing bite. It needed to be light enough to be carried on a neck that also had to be agile enough for rapid head movements during hunting. It needed to be strong enough to withstand the enormous stresses generated by its own bite force without cracking apart. And it needed to house and protect the most sophisticated sensory organs of any land predator, and those exceptional eyes and the grapefruit-sized olfactory bulbs that processed the most acute sense of smell in the dinosaur kingdom. The evolutionary solution was a skull that looks, at first glance, almost contradictory, massive and delicate at the same time, enormously heavy, up to 600 pounds in the largest individuals, and yet perforated with large openings called fenestrae that reduce that weight by roughly a third. Rigidly fused at every joint to resist the forces of its own bite, yet pneumatized internally with a honeycomb of tiny air chambers that made the bone lighter without sacrificing structural integrity. Every surface, every curve, every thickness of bone represents a compromise between competing demands: strength versus weight, protection versus mobility, power versus precision. Modern engineers call this optimization. They use computer algorithms to design structures that are simultaneously as strong and as light as possible, removing material where it isn't needed, adding it where it is, sculpting the shape to distribute stress evenly across the entire structure. T-Rex's skull is the result of the same optimization process, except it was carried out not by computers but by natural selection, over millions of years, testing each generation against the demands of killing and consuming the largest, most dangerous animals on Earth. The result was, in purely engineering terms, a masterpiece, a skull that could deliver more force per square inch than any other land animal that has ever lived, while simultaneously housing the sharpest eyes, the most sensitive nose, and some of the most rapid head-tracking neuromuscular reflexes in the history of terrestrial predators. It is, by any measure, the single most impressive piece of biological engineering that natural selection has ever produced in a terrestrial carnivore. In 2017, Paul Gignac of Oklahoma State University and Gregory Erickson of Florida State University published a study in the journal Scientific Reports that attempted to measure, as precisely as possible, the actual forces generated by T-Rex's jaws. Previous estimates had been made over the years, but many of them were, as paleontologist François Terrien of the Royal Tyrrell Museum noted, more theoretical constructs than grounded measurements. They weren't calibrated against living animals whose bite forces could actually be tested. Gignac and Erickson took a different approach. They started with crocodilians, the closest living relatives of dinosaurs outside of birds, animals whose bite forces can be directly measured in the laboratory. They lassoed real crocodiles, some as large as 17 feet, and got them to bite down on force-measuring instruments, essentially glorified bathroom scales. They then built three-dimensional anatomical models of the crocodile jaws, tested those models against the measured data, to see if their modelling approach was accurate, and once they were confident in the methodology, if they applied the same modelling technique to a CT-scanned replica of one of the best preserved T-Rex skulls, the bite force they calculated was approximately 7,800 pounds. Erickson described it in terms anyone could understand. That is like setting 3 small cars on top of the jaws of a T-Rex. That is basically what was pushing down. For reference, a human bites with about 200 pounds of force. An American alligator, one of the most powerful biters alive today, generates about 2,980 pounds. T-Rex was nearly 3 times stronger than that. But the raw bite force was only part of the story. What made T-Rex truly unique was what happened at the tips of those teeth, because the teeth were conical and deeply rooted, with rounded cross-sections rather than flattened blades. The enormous force of the jaws was concentrated on relatively small points of contact. The study calculated that the tip of each T-Rex tooth could exert a pressure of 431,000 pounds per square inch. That number is almost beyond comprehension. It means that when T-Rex bit down, the point of each tooth was driven into whatever it was biting with a pressure that could, and routinely did, punch clean through solid bone. This ability, called osteophagy, meaning bone eating, was almost unique among dinosaurs. Many large theropods had powerful bites, certainly enough to kill their prey. But they didn't eat the bones. They sliced off flesh, consumed the soft tissue, and left the skeleton more or less intact. T-Rex consumed everything, flesh, organs, and bone. It could bite through the pelvis of a triceratops, through the vertebrae of a hadrosaur, through the armoured plates of an ankylosaur, and the fossil record confirms this. A triceratops pelvis was found bearing nearly 80 individual T-Rex bite marks, with an entire region where the predator had repeatedly bitten down and removed sections of bone. This was not a single killing bite. This was methodical, sustained consumption of an entire skeletal element, bone and all. The ability to consume bone was not just a dietary quirk, it was an ecological superpower. In any ecosystem, the skeletons of dead animals represent an enormous reservoir of calories and minerals, calcium and phosphorus, locked inside a matrix of hydroxyapatite that most predators and scavengers simply cannot access. A lion can strip a carcass down to the bone, but it cannot eat the bone itself. A hyena can crack open the largest long bones to reach the marrow, but it cannot pulverize the shaft. The calories trapped inside the skeleton of a large herbivore, calories that could sustain a predator through lean times, are effectively wasted. T-Rex wasted nothing. Its ability to bite through, crush, and consume entire skeletal elements meant that it could extract calories from a carcass that every other predator in its ecosystem had to leave behind. A triceratops that had been killed and partially consumed by other predators still represented a massive food resource for an adult T-Rex, because the bones themselves, the parts that everything else had to leave, were food. This is the ecological equivalent of having a key to a pantry that nobody else can open. We can actually see this in the fossil record. The coprolites and the fossilized feces of large tyrannosaurs contain fragments of pulverized bone, ground to pieces small enough to pass through the digestive system. One coprolite attributed to T-Rex, found in Saskatchewan, was roughly 44 centimeters long and contained up to half its volume in bone fragments, including identifiable pieces of a young ornithischian dinosaur. The animal that produced this coprolite had not delicately picked the flesh from a carcass. It had consumed the animal nearly whole, bones and all, and processed the entire thing through a digestive system capable of extracting nutrients from material that would have been biologically inert to any other predator. This is what made T-Rex not just a predator, but an ecological processor, an animal that could convert an entire carcass, soft tissue and hard tissue alike, into usable energy. In an ecosystem with limited resources and intense competition, that ability was worth more than speed, more than stealth, more than any other single adaptation. A separate study published in 2012 by Carl Bates of the University of Liverpool and Peter Falkingham, then at the Royal Veterinary College, used a different modelling approach and arrived at even higher estimates for the back teeth. Their three-dimensional digital model of the T-Rex skull with reconstructed jaw musculature based on both bird and crocodilian anatomy predicted sustained bite forces of between 35,000 and 57,000 newtons at a single posterior tooth. That is roughly 7,800 to 12,800 pounds, depending on the position in the jaw and the modelling assumptions. By far the highest bite forces estimated for any terrestrial animal, living or extinct. Bates noted something else in his research that adds another layer to the story. The bite didn't just get strong, it got disproportionately stronger as the animal grew. This is called positive allometry, and it means that as T-Rex matured, its bite force didn't just increase in proportion to its size, it increased faster than its size. A T-Rex twice as heavy as another didn't have twice the bite force. It had more than twice the bite force. The jaw muscles, already enormous even for an animal of its colossal size, grew exponentially as the animal matured, filling out the widened temporal region at the back of the skull, the area behind the eyes that in T-Rex is massively expanded compared to other theropods. The implications of this growth pattern are significant. Juvenile T-Rex, and with their narrower skulls and proportionally weaker bites, were functionally different predators from adults. A study by Joseph Peterson of the University of Wisconsin, Oshkosh, and colleagues found that a 13-year-old T-Rex could generate a bite force of about 5,641 newtons, roughly the force exerted by a large hyena or a moderate-sized crocodile, strong enough to puncture bone, as the researchers demonstrated by replicating bite marks using a metal cast of a juvenile T-Rex tooth driven into cow bone, but not strong enough to crush bone. Not yet. The juveniles were developing their technique, building the jaw muscle strength that would eventually let them access food sources that no other animal in their ecosystem could touch. This is what paleontologists call resource partitioning, and it is one of the reasons T. Rex was so successful as a species. The juveniles, with their longer, lighter builds and their pursuit-oriented body plans, hunted different prey than the adults. They chased smaller, faster animals, the kind that a 9-ton adult would waste too much energy pursuing. The adults, with their bone-crushing jaws and their overwhelming power, targeted the largest herbivores in the ecosystem, the Triceratops and Edmontosaurus that no other predator could bring down. Parents and offspring weren't competing with each other for food. They were filling different roles in the same ecosystem, young and old, working the same territory without getting in each other's way. And now that we know, thanks to the 2025 Nanotyrannus study, that there was a completely separate species of smaller tyrannosaur occupying the same environment, and the picture becomes even more layered. Nanotyrannus was smaller, faster, with proportionally longer legs built for pursuit. Adult T-Rex was massive, slower, built for overwhelming force. Juvenile T-Rex fell somewhere in between. 3 tiers of tyrannosaur predator, each adapted to a different slice of the prey spectrum, all coexisting in the same ecosystem. This is a level of ecological complexity that we didn't even know existed until 2 years ago. The jaw of T-Rex was also shaped differently from other large theropods in a way that mattered. The tip of the upper jaw was U-shaped rather than V-shaped. Most carnivorous dinosaurs had V-shaped snouts, which concentrate the bite force on a narrower front end, useful for precision biting. The U-shaped jaw of T-Rex did the opposite. It widened the front of the mouth, increasing the amount of tissue and bone that could be ripped away in a single bite. The trade-off was increased stress on the front teeth, which is why T-Rex's premaxillary teeth, the ones at the very front, were smaller and differently shaped from the massive teeth further back. The front teeth gripped and tore, the back teeth crushed and pulverized. The skull bones themselves were fused and reinforced in ways not seen in other theropods. The nasals, the bones along the top of the snout, were fused together, eliminating any flexibility. In most large theropods, the skull bones retained some degree of mobility, a feature called cranial kinesis, which allowed the skull to flex slightly during biting, absorbing some of the stress. T-Rex had no such flexibility. Its skull was rigid, locked, every bone welded to its neighbours, and this made the skull heavier and less adaptable, but it also made it enormously strong. It could withstand forces that would have shattered a more flexible skull. It was built like a battering ram because it was used like one. Even the pneumatization of the skull, the honeycomb of tiny air spaces inside the bones that is common in theropods and serves to reduce weight, took on a different character in T-Rex. The air spaces were there, making the skull lighter than solid bone would have been, but the remaining bone was thicker, denser, more heavily reinforced. The weight saving from pneumatization was reinvested into structural strength. Every aspect of the engineering served the same purpose: to allow this animal to bite down with a force that could crush a car, deliver that force through teeth that could puncture through solid bone, and do so again and again and again without the skull breaking apart under the strain. This was not a scavenger's mouth. This was not the jaw of an opportunist that wandered from carcass to carcass. This was the single most powerful feeding apparatus ever evolved by a land animal, designed from the ground up for one purpose: to seize, kill, and completely consume the largest, most dangerous prey animals on Earth. And it worked. For roughly 2.5 million years, across an island continent stretching from what is now Alberta to Texas, T-Rex sat at the absolute apex of its food chain, unchallenged, seemingly perfect. But there was one part of this animal's anatomy that has puzzled and amused and frustrated scientists for generations, the feature that launched 1,000 jokes: the tiny arms. And the arms of Tyrannosaurus rex are the most mocked anatomical feature in the history of paleontology. They are the subject of internet memes, greeting cards, stand-up comedy routines, and casual dismissals by people who otherwise know very little about the animal. The assumption, the one embedded so deeply in popular culture that it has become almost reflexive, is that the arms were vestigial, useless, evolutionary leftovers that T-Rex was in the process of losing entirely, the way whales lost their hind legs or snakes lost their feet. Funny little appendages dangling from the front of an otherwise magnificent predator, too short to reach its mouth, too small to serve any meaningful purpose. This assumption is almost certainly wrong, and the reasons why reveal something important about how evolution actually works. And the first thing to understand is that T-Rex's arms were not weak. They were short, yes, disproportionately short relative to the animal's body size, absolutely. But short and weak are not the same thing. The muscles attached to those arms were substantial. A study of the arm biomechanics found that the M biceps muscle of T-Rex, the muscle that flexes the forearm, was approximately 3.5 times more powerful than the equivalent muscle in a human being. These were not atrophied remnants hanging limply from the shoulder. These were thick, powerfully muscled limbs packed into a compact frame, arms that could likely curl several 100 pounds with relative ease. Each arm ended in 2 clawed digits, large and curved and sharp, the kind of claws you would expect to find on an animal that used them for something. The joints were restricted, with the shoulder allowing only about 40 degrees of motion and the elbow only about 45 degrees, compared to the full rotation possible in a human shoulder and the 165 degrees of flexion in a human elbow. This limited range of motion has sometimes been cited as evidence that the arms were non-functional, but that interpretation misunderstands what limited range of motion actually means in a biological context. Consider the parallel jaws of a crocodile. They can open and close, and that is essentially all they can do. The range of motion is extremely limited compared to the human jaw, which can move laterally, forward, and backward. Nobody looks at a crocodile's jaw and concludes that it is vestigial, because of its limited range of motion. The limited range exists because the jaw is optimized for one specific task, a clamping down with overwhelming force, and any additional range of motion would compromise that function. The same logic applies to T-Rex's arms. The heavy build of the arm bones, the strength of the attached muscles, and the extremely limited range of motion all point to a system evolved to do one thing and do it well: grip something with enormous force and not let go. Paleontologists Kenneth Carpenter and Matt Smith, in the first detailed scientific description of T-Rex forelimbs, proposed exactly this. The arms may have been used to hold struggling prey while the jaws delivered the killing bite. A Triceratops being seized by a T-Rex would have been thrashing violently, its horns slashing, its body twisting, and an arm that could grip with several 100 pounds of force and resist being shaken loose through sheer mechanical rigidity would have been a meaningful advantage. Other hypotheses exist. The arms may have been used to push the animal up from a lying position, since a 9-ton biped lying on its side would need significant leverage to stand. They may have played a role in mating, providing grip or stabilization. They may have been used to hold food items against the body while the jaws tore off pieces. None of these hypotheses are mutually exclusive, and all of them are more consistent with the anatomical evidence than the popular notion that the arms serve no purpose at all. And here is the evolutionary argument that should settle the matter once and for all. Evolution is ruthlessly efficient over timescales of millions of years. Features that serve no function are not maintained. They are reduced, repurposed, or eliminated because maintaining them costs energy, and natural selection penalizes waste. The human appendix has shrunk because we no longer need it to digest cellulose. The eyes of cavefish have disappeared because vision is useless in total darkness. The hind legs of whales have been reduced to tiny internal bones because legs are a liability in water. If T-Rex's arms were truly vestigial, truly in the process of being eliminated by natural selection, we would expect to see them getting smaller and weaker over the evolutionary history of the Tyrannosaur lineage. And in a sense they did get smaller relative to body size. Earlier tyrannosaurs had proportionally longer arms, but the arms of T-Rex were not getting weaker, and they maintained strong musculature, sharp claws, and robust bone structure across millions of years. Evolution was reducing their length while preserving their strength. That is not the pattern of a feature being abandoned. That is the pattern of a feature being redesigned, optimized for a different function than it originally served, made shorter and more powerful and more rigid, like a tool being reshaped for a new task. The 2025 Nanotyrannus research added an illuminating data point to this discussion. One of the key anatomical differences between Nanotyrannus and T-Rex was the arms. Nanotyrannus had very long arms relative to its body, with a vestigial third finger, while T-Rex had short, powerful arms with only 2 fingers. These two tyrannosaurs living in the same ecosystem at the same time. He took completely different evolutionary approaches to their forelimbs. Nanotyrannus apparently found long arms useful for its hunting strategy, perhaps for grasping smaller, faster prey. T-Rex found short, immensely powerful arms useful for its hunting strategy, likely involving the restraint of much larger, more dangerous targets. The arms were not a joke. They were not an embarrassment. They were a specialized tool whose exact function we have not yet fully decoded, but whose engineering, thick muscles, sharp claws, rigid joints, consistent maintenance across millions of years of evolution, tells us that whatever they were doing, it mattered. They mattered enough for evolution to keep them, to invest metabolic energy in maintaining them, to build muscle and bone and claw generation after generation. One of the great ironies of the T-Rex's cultural legacy is that the feature people mock most is the feature that tells us the most about how much we still don't understand about this animal. The arms are a mystery, and in science, a mystery is not a punchline. It is an invitation. There is a broader lesson here, one that applies not just to T-Rex's arms but to the entire enterprise of understanding extinct animals. When we look at a feature we don't understand, our instinct is to dismiss it. If we can't immediately see the purpose, we assume there isn't one. We make jokes. We create memes. We treat the mystery as a deficiency, rather than recognizing it for what it actually is, evidence of our own ignorance. T-Rex's arms are not a joke about evolution. They are a reminder that this animal lived a life of immense complexity, and that it faced challenges and solved problems, and made use of every tool its body provided, and that we, looking back across 66 million years with nothing but fossilized bones and our own limited imaginations, have not yet figured out every detail of how it did so. The same humility applies to everything we have discussed tonight, and everything we are about to discuss. Every measurement, every estimate, every reconstruction is our best current understanding. Assembled from fragmentary evidence by brilliant, dedicated scientists using the most sophisticated tools available. But it is still incomplete. The growth curve that seemed settled for decades was dramatically revised in 2026. The Nanotyrannus question that seemed answered one way was definitively answered the opposite way in 2025. And the bite force estimates have been refined and revised multiple times as modelling techniques improved. This is not a weakness of the science. This is its greatest strength. The willingness to revise, to update, to say we were wrong and here is what we think now, is what separates real knowledge from dogma. And T-Rex, more than any other extinct animal, has been the testing ground for that process, the species against which paleontological methods are honed and refined and pushed to their limits. Every new technique in paleontology, from CT scanning to histological analysis to computational biomechanics, gets applied to T-Rex first, and every time it reveals something we didn't know. There is another mystery about the T-Rex that was only recently resolved, and its resolution rewrote decades of what scientists thought they knew about how this animal lived and grew and died. It concerns time. Specifically, how much time it took for a tiny feathered hatchling, small enough to hold in your hands, to become the largest predator on the continent. For decades, paleontologists thought they understood how Tyrannosaurus rex grew up. The story was clean, compelling, and widely repeated. A young T-Rex grew explosively, surging in size during a rapid growth spurt around the time of sexual maturity, reaching its full adult mass of 7 to 8 tons within about 25 years. It was a fast life and a hard one. The animals matured quickly, bred quickly, and most of them died before they reached old age, victims of injury, disease, or conflict with others of their kind. This story was based on a technique called paleohistology, the study of microscopic bone structure in fossils. Like the rings of a tree, dinosaur bones preserve annual growth marks, lines of arrested growth that form during seasonal slowdowns, recording the animal's age and growth rate year by year. By cutting thin cross-sections of fossilized leg bones and examining them under a microscope, researchers could count the growth rings, measure how far apart they were, and reconstruct how quickly the animal was growing at each stage of its life. The resulting growth curve showed a pattern that seemed clear. Slow growth in the early years, a dramatic spike in the teenage years, then a levelling off as the animal approached adult size. Maximum lifespan based on the oldest specimens was estimated at around 28 to 30 years. And it was a tidy picture. It was also, as a study published in early 2026 revealed, significantly wrong. Holly Woodward, a professor of anatomy and paleontology at Oklahoma State University and one of the world's leading experts in paleohistology, assembled the largest dataset ever compiled for T-Rex growth. 17 individual specimens, ranging from early juveniles to the most massive adults, representing the most comprehensive life history analysis ever conducted on the species. But Woodward didn't just add more specimens to the existing approach. She and her collaborators, including mathematician and paleobiologist Nathan Myhrvold and legendary paleontologist Jack Horner, developed new statistical methods to stitch together the fragmentary growth records from different individuals into a composite picture, and they examined the bone sections under a special kind of light, polarized light, which reveals hidden growth rings that standard microscopy had missed. The hidden rings changed everything. Previous studies had been undercounting. Growth rings that were too faint to see under normal light, compressed together during periods of slower growth, became visible under polarized microscopy. When Woodward's team incorporated these previously invisible rings into their analysis, the growth curve shifted dramatically. T. rex had not reached full size in 25 years. It had taken approximately 40 years, 15 years longer than anyone thought. The implications cascaded outward. If T. rex took 40 years to reach its full size of around 8 tons, then it was not the rapid growth prodigy that previous models had described, and it was a slow and steady grower, putting on mass gradually over 4 decades rather than surging to adult size in a meteoric adolescent spurt. This changes how we understand the animal's ecology, its behaviour, and its place in the ecosystem. As Jack Horner noted, a 4-decade growth phase may have allowed younger tyrannosaurs to fill a variety of ecological roles within their environments. That could be one factor that allowed them to dominate the end of the Cretaceous period as apex carnivores. Think about what this means in practical terms. A 10-year-old T-Rex and a 30-year-old T-Rex were not slightly different versions of the same animal. They were functionally different predators. The younger animal was lighter, faster, with a proportionally shallower skull and a weaker bite, adapted for chasing smaller prey. And the older animal was massive, slower, with a skull built for crushing bone and a bite force that could pulverize a pelvis. Between those two extremes lay a continuum of sizes and capabilities, each one occupying a slightly different niche in the ecosystem. A single species, spanning the ecological range that multiple species would cover in most modern ecosystems. This is resource partitioning taken to an extreme. In the modern African savanna, the role of small predator is filled by jackals and wild dogs, the role of medium predator by leopards and cheetahs, the role of large predator by lions. Each role is occupied by a different species with a different evolutionary history. In the Hell Creek ecosystem of late Cretaceous North America, T. rex may have been filling the equivalent of all those roles itself, and at different stages of its own life. Add in the separate species Nanotyrannus, confirmed in 2025, and you have a predator community that was layered, stratified, and far more complex than anyone imagined even a few years ago. The 2026 study also found something else that sent ripples through the paleontological community. 2 of the smaller specimens in the dataset, nicknamed Jane and Petey, had growth curves that didn't match any of the other T. rex in the study. Their growth patterns were, as Woodward carefully noted, potentially explainable by illness or injury, individual variation that threw off their development. But they could also indicate that these specimens represent a different species entirely. This finding dovetailed perfectly with the 2025 Nanotyrannus research. Lindsay Zano, who led the Nanotyrannus study, was not shy about connecting the dots. She noted publicly that this was the second study in just a few months, to support the conclusion that some specimens thought to be juvenile Tyrannosaurus are in fact a different animal altogether. The picture that emerges is humbling. For over a century, Tyrannosaurus rex has been the most studied dinosaur on Earth. More papers have been published about it, more specimens examined, more theories proposed and debated than about any other extinct animal, and yet as recently as 2025 and 2026, fundamental aspects of its biology were being dramatically revised. How long it took to grow up, how many species shed its ecosystem, which fossils actually belong to T. rex, and which belong to something else entirely. As Woodward herself said, even after more than a century of study, the Tyrannosaurus rex continues to surprise paleontologists, and there is one more number that puts all of this into perspective, a number that captures in a single figure the sheer scale of T. rex's presence on the planet. In 2021, a team led by Charles Marshall at the University of California, Berkeley, attempted something that one of the most influential paleontologists of the 20th century George Gaylord Simpson had said was impossible. They tried to estimate how many T-Rex had ever existed, not the number alive at any one time, but the total number of individuals that had been born, lived, and died over the entire history of the species. Marshall's team used a relationship from ecology called Dammoth's Law, which links an animal's body mass to its population density. Larger animals, requiring more food and more territory, exist at lower densities than smaller ones. Using estimates of T-Rex's average body mass, approximately 5,200 kilograms or 5.2 tons as an ecological average across all age classes, combined with data on when the animal reached sexual maturity, around 15.5 years old, and its maximum lifespan, probably into its late 20s or early 30s, based on the pre-2026 data and the total geographic range of the species, estimated at about 2.3 million square kilometers across western North America. They ran Monte Carlo simulations to generate a population estimate. The number they arrived at was roughly 20,000 adult T-Rex alive at any given time. One dinosaur per 100 square kilometers. 2 in an area the size of Washington, D.C., about 3,800 in an area the size of California. That may not sound like many, and it isn't, and by the standards of any modern large predator, except perhaps the most rare. But T-Rex existed as a species for approximately 2.5 million years. Over that span, across roughly 127,000 generations, the total number of individual T-Rex that lived and died adds up to approximately 2.5 billion, 2.5 billion tyrannosaurs. Over the course of the species' existence, 2.5 billion of these animals hatched from eggs, grew through their long adolescence, hunted and fought and mated and died across an island continent, their bones sinking into the mud, their flesh recycled back into the ecosystem, their lineage continuing until a rock from space ended everything. Of those 2.5 billion individuals, fewer than 100 have ever been found as fossils. Many of those are represented by a single bone or a fragment of a jaw. Only about 32 relatively well-preserved post-juvenile specimens sit in public museums today. That means we have recovered approximately 1 T-Rex for every 80 million that existed. The vast, overwhelming majority of every T-Rex that ever lived left no trace at all, no bone, no tooth, no footprint. They existed completely and utterly, and then they vanished into deep time as though they had never been. If the T-Rex population had been 2.5 million instead of 2.5 billion, Marshall noted, then we would probably never have known they existed at all. There is something almost vertiginous about that thought. This animal, the most famous creature in the history of paleontology, the one species that every child on Earth can name, exists in our awareness only because enough of them lived and died over a long enough span of time that a tiny, statistically insignificant fraction of their bones happen to be preserved in conditions conducive to fossilization, and then happen to be exposed by erosion at the surface, and then happen to be found by one of the relatively small number of human beings who are looking for them. We know T-Rex at all only through an almost miraculous chain of unlikely events, and yet from that tiny sample, from those 32 good skeletons scattered across the museums of the world, we have reconstructed an animal with 13 times our visual acuity, a nose rivaling a cat's, the most powerful bite in terrestrial history, and a 40-year growth curve that turned a single species into an entire predator community. The science is remarkable, but the gaps in our knowledge are even more remarkable, because they remind us of how much is still out there, hybrid in the rock, waiting. Consider for a moment the journey of a single T-Rex across its lifetime based on what we now know. It begins as an egg, not a large egg by dinosaur standards, perhaps 40 to 50 centimeters long, laid in a nest scraped into the warm earth of a floodplain. We do not have confirmed T-Rex nests, but we have nests from other tyrannosaurs, and they suggest that the parents provided some degree of care, at least during incubation. The egg hatches, and what emerges is not a miniature version of the adult. It is something quite different. Small, perhaps the size of a turkey covered in downy filamentous feathers, with proportionally longer legs and a narrower skull than the adult form. Its eyes are large relative to its head. Its jaws are equipped with small, sharp, slicing teeth rather than the massive crushing teeth it will develop decades later. For the first several years of its life, this juvenile T-Rex is a small, fast, agile predator. It hunts lizards and small mammals and insects. It avoids larger predators, including adult T-Rex, which were probably not above killing and eating juveniles of their own species. It grows steadily, but not spectacularly, adding mass year by year, its skull gradually deepening, its jaws gradually strengthening, its body gradually shifting from the slim, pursuit-adapted build of a juvenile toward the heavy, power-adapted build of an adult. By the time it is a teenager, perhaps 12 or 13 years old, it is already a formidable animal, several meters long, capable of biting through the bone of smaller prey. It is beginning to target larger animals, in moving up through the size classes of available prey as its growing body opens new ecological possibilities. It is, in effect, a different species of predator every few years, competing for food not with adults of its own kind, but with whatever prey species falls within its current size and capability range. This continues for decades. Decade after decade, the animal grows. Its skull widens. Its jaw muscles expand. Its bite force increases disproportionately, outpacing its body mass. By the time it reaches its mid-30s, approaching the full adult size of 8 tons, it has transitioned completely from pursuit predator to power predator. The animals it hunted as a teenager are now too small to bother with. Its targets now are the Triceratops, the adult Edmontosaurus, the Ankylosaurus. The most dangerous animals in its ecosystem are the ones that no other predator can touch. And then, if it is lucky, if it avoids the injuries and infections and conflicts that killed most tyrannosaurs before they reached old age, it lives on for a few more years, perhaps into its early 40s, perhaps longer. We don't know the true maximum lifespan because so few individuals survive to old age, and the 2026 study suggests we may have been underestimating longevity as well as growth time. As Thomas Cullen, a paleontologist at Auburn University, noted, we may be underestimating longevity in this species. The entire arc, from egg to apex predator, took 40 years, and every year of it, every stage, every transition from one body plan to another, was a story of adaptation, of an animal reshaping itself in response to the demands of its environment, it becoming a different kind of predator with each passing decade. And here is perhaps the most astonishing implication of the population study. If we have found one in every 80 million T-Rex that ever existed, and if many of the specimens we have found are fragmentary or poorly preserved, then the overwhelming majority of T-Rex biology, behavior and variation is simply invisible to us. We are drawing our picture of this animal from an absurdly tiny sample. Consider what this means for everything we have discussed tonight. The bite force estimates are based on a handful of skulls, each one a single individual drawn from a population of billions. The growth curves are based on 17 specimens out of 2.5 billion. The visual acuity estimates are based on skull geometry from a few dozen individuals. Every number, every measurement, and every claim we have made is an extrapolation from a sample so small relative to the total population that it would be laughed out of any other field of science. And yet, the numbers are consistent. The bones tell the same story over and over. The growth rings show the same patterns. The skull geometry falls within the same range. The bite marks on prey bones are consistent across multiple sites and multiple specimens. The picture we have assembled from these fragments is almost certainly close to the truth, because the fragments all agree with each other. But the margins of what we don't know, the questions we can't answer, the individual variation and behavioural complexity and ecological nuance that is lost to us. Those margins are vast. Every T-Rex that did not fossilise took its secrets with it, and every individual that lived and died without leaving a single bone in a single formation carried a unique story, a unique set of experiences, a unique life trajectory from egg to adult that we will never know about. The fossil record gives us the outline. It gives us the general shape of the animal and its world. But the details, the million small truths that made each T-Rex an individual rather than a specimen, those are gone. And that, perhaps more than any single fact about its eyes or its nose or its jaws, is what makes T-Rex so endlessly fascinating. We know enough to be astonished. We know too little to be satisfied. And the gap between those two states is where science lives, always reaching, always revising, always finding one more bone and one more cliff face that changes the story just enough to send everyone back to the beginning. To truly understand T-Rex, though, you cannot look at the animal in isolation. You have to understand the world it lived in, the ecosystem that shaped it and was shaped by it, the web of relationships that made T-Rex not just a predator, but the keystone of an entire community of life. The best window we have into the world of T-Rex is a place called the Hell Creek Formation, a layer of rock stretching across Montana, the Dakotas, and Wyoming that preserves the last 2 to 3 million years of the Cretaceous in extraordinary detail. When paleontologists dig there, they don't just find isolated bones. They find an entire community of life frozen in stone, predators and prey, giants and miniatures, and creatures of land and water and air, all layered together in sediments that record not just individual animals, but the relationships between them, the ecosystem they shared, the world as it actually was in the final chapter of the age of dinosaurs. That world was profoundly different from anything you have experienced. Start with the geography. North America in the late Cretaceous was not one landmass. It was two, divided by a body of water called the Western Interior Seaway, a warm, shallow sea that stretched from what is now the Gulf of Mexico all the way to the Arctic Ocean, cutting the continent in half. The eastern portion, called Appalachia, was a low-lying island landmass about which we know relatively little because the geological conditions there were poor for fossil preservation. The western portion, called Laramidia, is where T-Rex lived, a relatively narrow strip of land running from Alaska to Mexico, flanked on one side by the rising Rocky Mountains and on the other by the warm waters of the Seaway. Laramidia was smaller than you might expect. Despite being the home of some of the largest land animals in Earth's history, it was not a vast, sprawling continent. It was more like a very large island, perhaps comparable in area to modern Australia, compressed between mountains and sea, and yet within that limited space it supported an astonishing density of enormous animals. The air was different. Carbon dioxide levels were roughly 4 times what they are today, driving a greenhouse effect that kept the planet warm from pole to pole. There were no ice caps, not at the North Pole, not at the South Pole. The sea levels stood perhaps 170 metres higher than modern oceans, drowning coastal plains and creating vast networks of shallow inland waterways. The global average temperature was significantly warmer than today, and even the high latitudes experienced only mild winters. Crocodilians lived above the Arctic Circle. Forests grew where Antarctic ice sheets now grind against bedrock. Into this warm, wet, CO2-rich atmosphere grew vegetation that was lush beyond anything the modern temperate world can match. The forests of the Hell Creek Formation were dominated by flowering plants, the angiosperms, which had been spreading and diversifying throughout the late Cretaceous. Ferns carpeted the forest floor, towering conifers provided the canopy, and among them grew the early representatives of families we would recognize today, and ancestors of magnolias and palms and sycamores, their flowers attracting insects, their fruits being eaten and dispersed by the animals that lived beneath them. This was the stage. Now meet the cast. The most abundant large animal in the Hell Creek ecosystem by a wide margin was not T-Rex, it was Triceratops. Paleontologist Robert Bakker once estimated that Triceratops bones make up 5/6 of all large dinosaur fossils recovered from late Cretaceous North America. If that proportion is even approximately correct, and the general observation that Triceratops fossils vastly outnumber those of any other large species is accepted by virtually all paleontologists working in the formation, then we need to fundamentally reconsider what the Cretaceous landscape actually looked like. Forget the images of lone Triceratops grazing quietly in a clearing. Think instead of the Great Plains, before European contact, when bison herds stretched from horizon to horizon, when the ground trembled under the weight of millions of animals, when you could travel for days without seeing anything but grass and grazing bodies. Now replace every one of those bison with a 3-horned, 9-meter-long tank, weighing up to 9 tons, with a skull that comprised 1/3 of its entire body length, with 2 brow horns each nearly a meter long that could gore a tyrannosaur, and a frill of solid bone protecting its neck and shoulders. That was Triceratops, the American bison of the Cretaceous, except armoured like a medieval knight. These animals moved in herds. The sheer abundance of their fossils, often found in concentrated bone beds representing multiple individuals, suggests large social groups. A herd of Triceratops would have been a formidable sight. Hundreds of horned heads turned outward, a wall of bone and horn that even a full-grown T-Rex would approach with caution. The horns were not decorative, they were weapons. Studies of Triceratops skulls have found healed puncture wounds in the frills consistent with combat, either between rivals or against predators. Some of those wounds match the diameter of T-Rex teeth. Alongside Triceratops lived the hadrosaurs, the duck-billed dinosaurs, represented in the Hell Creek formation primarily by Edmontosaurus. These were large herbivores in their own right, reaching lengths of 12 meters or more, but they lacked the armor and weaponry of Triceratops, and their advantage lay in their teeth. Hadrosaurs had evolved the most sophisticated plant processing apparatus of any dinosaur lineage, dental batteries containing hundreds of interlocking teeth stacked in columns, constantly being replaced from below as the upper surfaces wore down. These grinding mills could process tough fibrous vegetation with an efficiency that no other dinosaur could match, allowing hadrosaurs to exploit food sources that were too tough for other herbivores to digest. Edmontosaurus herds likely numbered in the thousands, moving across the floodplains in seasonal patterns, their sheer numbers providing a measure of safety against predation. When you are one animal in a group of 2,000, the odds that you specifically will be the one selected by a hunting tyrannosaur are reassuringly small. And then there was Ankylosaurus, the armoured fortress. Its body was covered from head to tail in bony plates called osteoderms, embedded in the skin like a suit of chainmail. Its back was a mosaic of interlocking armour. Its tail ended in a massive club of fused bone that biomechanical studies have estimated could be swung with enough force to shatter the leg of a predator. Ankylosaurus was not fast. It did not need to be. It was a walking tank, and any predator that wanted to make a meal of it had to find a way past armour that could resist the most powerful bite on Earth. Smaller herbivores filled out the lower tiers of the ecosystem. Pachycephalosaurus, with its dome of solid bone atop its skull, the purpose of which is still debated. Some paleontologists favouring the headbutting hypothesis, others suggesting display or species recognition. Thescelosaurus, a smaller ornithopod that browsed in the undergrowth. Leptoceratops, a diminutive relative of Triceratops, no larger than a pig, probably filling a niche similar to modern deer. In the rivers and lakes and swamps that threaded through the Hell Creek landscape, another community of life flourished. Crocodilians, some of them enormous, patrolled the waterways. Deinosuchus, a truly gigantic crocodilian that lived slightly earlier in the Cretaceous, could reach lengths of 10 meters or more. but even the smaller crocodilians of the Hell Creek were formidable animals, occupying the freshwater apex predator niche the same way their modern descendants do today. Turtles of various sizes populated the margins, some of them large enough to weigh several 100 pounds. Fish filled the waters, from small schooling species to large predatory forms. Above this world flew the pterosaurs, those remarkable flying reptiles that were not dinosaurs but shared the sky with them. The largest known pterosaur from the late Cretaceous, Quetzalcoatlus, had a wingspan of roughly 11 meters, wider than a small airplane. Standing on all fours, it would have looked a giraffe in the eye, yet its bones were hollow, honeycomb-light with air pockets, and a creature the size of a small aircraft probably weighed only about 250 kilograms. It likely hunted by stalking across floodplains on folded wings like a giant stork, snatching up small animals with a beak the length of a human arm. And in the canopy and the understory, birds were present. Real birds, of the kind that would survive the coming extinction and eventually inherit the sky. They were not the dominant aerial animals of the Cretaceous. That title belonged to the pterosaurs, but they were there, diversifying, occupying niches that their pterosaur cousins didn't fill. Small, agile, many of them insectivorous or frugivorous, they represented the one branch of the dinosaur family tree that would survive the catastrophe to come. If you could have stood in a Hell Creek forest and listened, you would have heard birdsong. Not the same songs you hear today, not the robins and sparrows and warblers of the modern world, but something recognizably bird-like, high and liquid and strange, drifting down from the canopy of a world that had no idea it was about to end. Salamanders and frogs occupied the margins between water and land. Insects filled every remaining gap, ants and bees and beetles co-evolving with the flowering plants in pollination partnerships that were being established for the first time. The same fundamental relationships between plants and insects that sustain modern ecosystems today. The picture that emerges is not a simple world with a few large dinosaurs wandering through empty space. It is a dense, layered, interconnected community comparable in complexity to the most species-rich environments on modern Earth. And in the shadows, beneath the feet of the giants, the mammals persisted. They had been there all along, evolving alongside the dinosaurs for over 150 million years. But they were small. The largest known Cretaceous mammal from North America was perhaps the size of a badger. Most were the size of mice or rats, nocturnal and secretive, hunting insects and seeds in the ecological margins that the dinosaurs didn't fill. They were not failures. They were highly successful at what they did. But what they did was stay out of the way. This was the ecosystem that T-Rex sat atop. Not a simple food chain with a single predator at the top and a single prey species below, but a complex multi-layered community of dozens of species, each filling its own role, each connected to the others through a web of relationships that had been refined over millions of years. T-Rex was the apex, the keystone, the animal around which the entire ecosystem organized itself. Its presence shaped the behavior of every other species in the community. The herding behavior of Triceratops was in part a response to tyrannosaur predation, and the armor of Ankylosaurus evolved under the selective pressure of being hunted by something with a 7,800-pound bite. The speed of Edmontosaurus, the vigilance of the smaller herbivores, the nocturnal habits of the mammals, all of these traits were influenced directly or indirectly by the presence of T-Rex, and T-Rex was shaped in return. Its extraordinary vision was honed by millions of years of pursuing prey that was learning to see it coming. Its bite force was driven to extremes by the armor of the animals it hunted. Its growth pattern, with juveniles filling different ecological roles than adults, was an adaptation to an ecosystem so densely packed with large herbivores that there was room for predators at every size class. Predator and prey evolved together. They locked in an arms race that drove both sides to ever greater extremes of adaptation. T-Rex's teeth grew sharper and its bite grew stronger because Triceratops's armour grew thicker and its horns grew longer. Triceratops's armour grew thicker and its horns grew longer because T-Rex's bite grew stronger and its teeth grew sharper. Each animal, in a very real sense, created the other. This is what ecologists call coevolution, and it is one of the most powerful forces in biology. It produces results that seem almost absurdly over-engineered, predators that are too strong, and prey that is too armoured and teeth that are too sharp, until you realise that every feature exists in response to something else, and the whole system is in balance, each extreme justified by the opposing extreme that provoked it. And the Hell Creek ecosystem was the culmination of 165 million years of dinosaur evolution. Every species in it was the product of hundreds of millions of years of the trial and error, of lineages tested and refined and tested again, of adaptations stacked upon adaptations until the result was a community of life so intricate and so finely tuned that removing any single element, as the asteroid would soon demonstrate, could cause the entire structure to collapse. But before that collapse, in the final few million years before the sky burned and the darkness came, the Hell Creek was alive in a way that our modern world can barely approximate. The biomass of large animals per square kilometre almost certainly exceeded anything we see today. The diversity of species, the complexity of the food web, the sheer density of enormous living things packed into a warm, fertile landscape was unlike anything the modern world can match. There was also a temporal dimension to this ecosystem that is easy to overlook. The community of life preserved in the Hell Creek Formation was not static. It changed over the 2 to 3 million years that the formation spans. Species appeared and disappeared. Populations waxed and waned. The balance of predators and prey shifted subtly as climate fluctuations, sea level changes, and the slow drift of continents altered the landscape. T-Rex itself was part of this flux. The species we call Tyrannosaurus rex appears in the fossil record roughly 68 to 66 million years ago, a span of about 2 million years, but the Tyrannosaur lineage extends much further back. T-Rex did not appear from nothing. It descended from a long line of tyrannosaurs that had been evolving across Laramidia for tens of millions of years, each generation slightly different from the last, each one shaped by the ecosystem it inhabited. The T-Rex that lived 68 million years ago and the T-Rex that lived 66 million years ago may have been subtly different, separated by roughly 1 million years of evolutionary change, hundreds of thousands of generations, each one a slight revision of the model before it. We tend to think of species as fixed things, as though Tyrannosaurus rex was a single, unchanging design rolled off an assembly line. In reality, like every species that has ever existed, it was a living, evolving, continuously changing lineage, a river of genes flowing through time, adapting to whatever conditions it encountered. The T-Rex that died in the extinction was not the same animal, genetically or ecologically, as the T-Rex that first evolved. It was the latest model, the most recent iteration, the version that happened to be alive when the asteroid arrived. The 2025 confirmation that multiple tyrannosaur species coexisted in the final million years of the Cretaceous hints at a level of predator diversity that we are only beginning to appreciate. Nanotyrannus, with its 2 newly confirmed species, represents just the beginning. There may be other species, other lineages, other variations hiding in museum collections and unexcavated formations, waiting for the next generation of paleontologists to find them. The story of T-Rex's world is not finished being written, and at the centre of all of it, watching with eyes that could see for miles, and smelling the wind with a nose that could detect blood and fear, and the chemical signature of a herd of Triceratops moving through the valley below, was Tyrannosaurus rex. Not a monster, not a movie prop, a real animal, embedded in a real ecosystem, playing a role that no other animal has ever played before or since. The most formidable predator the land has ever known, living in the most complex terrestrial ecosystem the planet had ever produced. Take a moment with that. Let the scale of it settle. We talk about ecosystems in the abstract, as though they were diagrams in a textbook, arrows connecting boxes with species names in them. But the Hell Creek was not an abstraction. It was a living, breathing, roaring, rustling, buzzing, growing, dying, decaying world, as real and as vivid as the one outside your window right now, just incomprehensibly older. The soil was warm. The rivers ran clear. The air smelled of magnolia blossoms and rotting wood, and the faintly metallic tang of something enormous that had died upstream and was slowly being returned to the earth by a billion tiny organisms. And through all of it, for 2.5 million years, T-Rex walked. Generation after generation, 127,000 generations in total, each one born and raised and taught to hunt, and left to find its place in a world that demanded constant vigilance and rewarded only competence. Not intelligence as we understand it, not planning or philosophy or self-awareness, just competence. The ability to detect, to pursue, to kill, to consume, to survive long enough to produce the next generation and start the cycle again. 2.5 billion times that cycle completed, and 2.5 billion T-Rex drew their first breath and eventually their last. And the world kept turning, indifferent to each individual story, concerned only with the continuation of the pattern. Which brings us to what the movies got wrong, because for all the spectacle that Hollywood has given us, the real T-Rex was stranger, more dangerous, and more alien than anything Steven Spielberg ever imagined. The Tyrannosaurus Rex that lives in your imagination is a creature that never existed. It is a composite, assembled from a century of films, television documentaries, museum displays, and children's books, and nearly every element of that composite is either a distortion, a simplification, or an outright invention. We have already dismantled some of these myths, the vision based on movement nonsense, and the idea that the arms were useless, the assumption that T-Rex reached full size in a couple of decades. But there are more, and they are worth addressing because they reveal just how far the gap has grown between what science knows and what the public believes. Start with the roar. You know the sound. The deep, thundering, almost mechanical bellow that T-Rex produces in every film, the sound that shakes the leaves and rattles the bones of everyone within earshot. It is one of the most iconic sound effects in movie history. The original Jurassic Park roar was famously created by mixing recordings of a baby elephant, a tiger, and an alligator, processed and layered to produce something that felt massive and primal and terrifying. It is almost certainly nothing like the sound T-Rex actually made. The closest living relatives of T-Rex are birds and crocodilians. Birds produce vocalizations using an organ called the syrinx, located at the junction of the trachea and bronchi. Crocodilians produce deep resonating bellows and hisses using their larynx and a set of vocal structures quite different from those of mammals. Neither group produces the kind of open-mouthed lion-like roar that Hollywood has associated with T-Rex. Based on the skull morphology, the structure of the inner ear, and the vocalizations of its closest living relatives, many paleontologists believe T-Rex more likely produced deep, low-frequency sounds, rumbles and booms and closed-mouth vocalizations that would have travelled enormous distances through the thick, humid air of the Cretaceous. Think less of a lion roaring and more of a crocodilian bellow, a sound that you feel vibrating in your chest before you consciously hear it. Low-frequency infrasound that could propagate through dense vegetation, through fog, through darkness, announcing the presence of the animal over distances of kilometres. This is in some ways more unsettling than the movie roar. A roar tells you where the danger is, a low, pervasive vibration that you feel in your sternum without being able to locate its source. That is something else entirely. Now consider speed. The Jurassic Park chase scene, where T-Rex pursues a jeep at highway speeds, is one of the most thrilling sequences in cinema history. It is also, by the current scientific consensus, an exaggeration. Biomechanical modelling and analysis of T-Rex's leg structure, body mass, and the physical forces involved in locomotion suggests that T. rex probably could not run in the technical sense, meaning it could not achieve a gait in which all feet were off the ground simultaneously. Computer models and track evidence suggest that T-Rex walked briskly, at speeds up to roughly 15 miles per hour, or about 25 kilometers per hour. That is faster than a human jog, but significantly slower than a sprinting human, and nowhere near the 30+ miles per hour suggested by the movie. But here is the detail that the movies don't tell you, and it changes the entire calculus. 15 miles per hour doesn't sound terrifying until you realize that most of T-Rex's prey was even slower. The large herbivores of the Hell Creek Formation, the Triceratops, the Edmontosaurus, the Ankylosaurus, were not built for speed either. They were massive, heavy, armoured or herding animals whose survival strategy was based on size, numbers and defensive weaponry, not on outrunning predators. T-Rex didn't need to be fast in absolute terms. It needed to be faster than what it was hunting. And it was. A full-grown T-Rex walking at 15 miles per hour toward a 9-ton Triceratops that could manage perhaps 10 or 12 miles per hour at a dead run was not in a desperate sprint. It was in a steady, inevitable pursuit, closing the distance gradually, relentlessly, with the patience of an animal that knew it would catch what it was chasing. Then there is the question of feathers. The clean, scaly, reptilian skin of every film T-Rex is almost certainly a simplification, and increasingly a misleading one. We know with certainty that many dinosaurs closely related to T-Rex were feathered. One of the most dramatic example is Yutyrannus wally, a large tyrannosaur from the early Cretaceous of China, approximately 9 meters long, whose fossilized remains preserved clear evidence of extensive filamentous plumage covering much of its body. Yutyrannus was not a direct ancestor of T-Rex, but it was a close relative, and it demonstrates that feathered body coverings were present in the Tyrannosaur lineage well before T-Rex evolved. Whether T-Rex itself was feathered remains debated. Some skin impressions from large tyrannosaurs show scaly textures, leading some researchers to propose that the largest adults may have lost their feathers as they grew, the way modern elephants have largely lost the body hair of their smaller ancestors, because the thermal dynamics of a very large body make insulation unnecessary or even counterproductive. Others argue that T-Rex may have retained feathers on parts of its body, perhaps the back or the head, while having bare skin on the belly and sides for thermoregulation. The truth is that we don't yet have enough skin impression data from T-Rex itself to resolve the question, but we can say with confidence that the image of T-Rex as a uniformly scaled, bare-skinned reptile is, at minimum, an oversimplification. The juveniles, smaller and more heat-vulnerable, were very likely feathered. The adults may or may not have been, in whole or in part. What we can say for certain is that T-Rex descended from feathered ancestors, and that feathers in some form were part of its evolutionary heritage. And there is one more myth worth addressing, because it speaks to a deeper misunderstanding about what dinosaurs were. The common image of T-Rex, and of dinosaurs in general, places them in a world that is barren, volcanic, and vaguely apocalyptic. Scorched earth, smoking craters, leafless trees silhouetted against an orange sky. The Cretaceous in the popular imagination looks like the aftermath of a nuclear war. This is almost entirely a creation of mid-20th century illustration, when paleoartists working with limited information and unlimited dramatic instinct painted dinosaurs against the most extreme backdrops they could imagine. The real, late Cretaceous was nothing like that. It was one of the most lush, verdant, biologically productive periods in Earth's history, and the Hell Creek landscape was covered in dense forests of flowering plants, magnolias and sycamores and palms, interspersed with conifers and carpeted with ferns. The air was warm and humid, rich in carbon dioxide, thick with the scent of flowers and decaying vegetation and the constant hum of insects, Rivers braided across broad floodplains. Lakes and swamps dotted the low-lying areas. The vegetation was so abundant that it supported herds of multi-ton herbivores in densities that would rival the Serengeti. T-Rex did not live in a wasteland. It lived in a garden. A warm, wet, impossibly fertile garden teeming with life at every scale, from the bacteria in the soil to the 9-ton Triceratops herds that flowed across the landscape like living rivers. Understanding this, and seeing the world as it actually was rather than as Hollywood painted it, changes how you think about the animal. T-Rex was not a survivor clinging to existence in a hostile world. It was the apex predator of one of the richest ecosystems the planet has ever produced, thriving at the centre of an abundance that we can barely imagine. And finally, intelligence. The 1993 Jurassic Park portrayed T-Rex as a mindless force of nature, all power and appetite with no evident capacity for thought or strategy. The more recent Jurassic World films went further in the opposite direction, depicting T-Rex as something almost heroic, capable of what looks suspiciously like decision-making and even cooperation with humans. The truth lies somewhere in between, and it is more interesting than either extreme. T-Rex's brain, relative to its body size, it was not large. It was smaller proportionally than the brains of modern mammals of comparable size. But raw size ratios can be misleading. The brain regions devoted to sensory processing, smell, vision, balance, and coordinated movement were disproportionately enlarged. This was not the brain of a philosopher, but it was also not the brain of an automaton. The enhanced sensory processing we discussed earlier, the extraordinary vision and smell and hearing, all required significant neural infrastructure to interpret. An animal that can track a scent for miles, resolve fine detail at 6 kilometers, and coordinate its eye and head movements for precision tracking is not operating on simple instinct alone. It is processing enormous amounts of sensory information in real time and making decisions based on that information, and which prey to pursue, which to avoid, how to approach, when to strike. Was T-Rex intelligent in the way we use the word for humans, or even for crows and dolphins? Almost certainly not. The cognitive structures that support abstract reasoning, tool use, and self-awareness are not evident in the Tyrannosaur endocast. But was it significantly more cognitively capable than the lumbering movie monster that runs into things and is outwitted by children? Almost certainly yes. It was a capable predator with a specialized brain, evolved over millions of years to process the sensory world with exquisite precision and to act on that information with lethal efficiency. Not a mindless brute, not a calculating genius, something in between, something tailored by evolution to be exactly as intelligent as it needed to be to do the most difficult job in its ecosystem, hunting and killing the largest, most dangerous animals on Earth. We should also pause to address the question of hearing, because the popular image of T-Rex as a strictly visual and olfactory hunter misses a third channel that may have been equally important now in certain conditions. The inner ear structures of T-Rex, as revealed by CT scanning, show a cochlear and semicircular canal arrangement consistent with good low-frequency hearing. This isn't surprising. Low-frequency sound travels much further than high-frequency sound, especially through dense vegetation and humid air, in the forests and floodplains of the Hell Creek, where sight lines were often obstructed by vegetation and wind could carry scent in unpredictable patterns. The ability to detect and localize low-frequency sounds would have been a crucial complement to vision and smell. Modern elephants communicate using infrasound, vocalizations below the range of human hearing that can travel for kilometers through the ground and the air. Crocodilians produce deep resonating bellows that serve as territorial signals and mating calls. If T-Rex produced similar low-frequency vocalizations, and the structure of its skull and inner ear strongly suggests that it did, then the soundscape of the late Cretaceous would have included something we modern humans would find deeply strange. A constant low, barely perceptible rumble carrying across the landscape, inaudible to most small animals but perfectly clear to anything with the right ears, a network of tyrannosaur calls communicating territorial boundaries, reproductive status, and perhaps much more across distances of kilometres. You would not have heard them. You would have felt them. The movies gave us a T-Rex that was, in almost every respect, less than the real thing. Less visually capable, less olfactory capable, less acoustically accurate, less ecologically complex, and far less strange than the animal that actually existed. The real T-Rex, the one that walked the Hell Creek floodplains 68 million years ago, the one that could see you from 4 miles away and smell you from further, the one that bit through solid bone with 431,000 pounds per square inch of tooth pressure. You're the one that took 40 years to grow up and belonged to a species that numbered 2.5 billion over its history, was more extraordinary than any screenplay could capture. And now, as we near the end of this story, there is one more thing to consider, something that puts all of it, the eyes and the nose and the jaws and the arms and the growth and the ecosystem, into a final humbling perspective. 66 million years ago, a rock the size of a mountain struck the shallow seas of the Yucatan Peninsula, and the world that we have been exploring tonight ended, not slowly, not gently, with an explosion that released the energy of 100 million nuclear weapons, that vaporized billions of tons of rock and sulfur and seawater, and that launched a shroud of debris into the stratosphere that blocked the sun for a year and dropped global temperatures by nearly 30 degrees Celsius. The plants died first, then the herbivores that depended on them, then the predators that depended on the herbivores. Within a geological instant, 3/4 of all species on Earth were gone. T-Rex, with its unmatched eyes and its acute nose and its bone-crushing jaws and its 4-decade journey from hatchling to giant, was among them. The most sophisticated terrestrial predator the planet had ever produced was powerless against 10 kilometres of carbonaceous chondrite and iron arriving at 20 kilometres per second. All of that evolutionary refinement, all of those millions of years of incremental improvement, and all of those 2.5 billion individuals that had lived and hunted and died across an island continent, ended in an afternoon. The thin layer of iridium-rich clay that marks the boundary between the Mesozoic and Cenozoic eras, the geological signature of the impact, is the dividing line between the world of T-Rex and the world of everything that came after. On one side, the most complex terrestrial ecosystem the planet had ever assembled. On the other, devastation, followed by a long, slow rebuilding that would eventually produce the world we know, a world of mammals and birds and flowering plants, of grasslands and ice ages, and eventually, improbably, of a species of primate that would dig into the rock 66 million years later and discover what had been there before. And the fossil record's humility is worth dwelling on as you settle in for the night. Of the 2.5 billion T-Rex that lived over the span of their species' existence, we have found fewer than 100 individuals. Most of those are represented by a single bone, a fragment of a jaw, a tooth worn smooth by 66 million years of sediment pressure. Only about 32 relatively well-preserved post-juvenile skeletons sit in the museums of the world, available for study, one specimen for every 80 million that existed. The overwhelming majority of T-Rex left no trace at all. They lived, completely and utterly, and then they were gone, dissolved back into the chemistry of the earth, their bones ground to dust by the weight of the ages, their stories lost. And yet from those 32 good skeletons, from those fragments and teeth and weathered bones, my science has reconstructed an animal of staggering sophistication, an animal whose visual acuity may have exceeded that of any living bird of prey, whose sense of smell rivaled a house cat, whose bite was the most powerful ever measured in a terrestrial animal, whose 40-year growth curve turned a single species into an entire hierarchy of predators, whose ecosystem was so complex that we are still discovering new species within it, as recently as 2025. Every few years a new study arrives and changes what we thought we knew. The Nanotyrannus confirmation in 2025 rewrote the story of who shared T-Rex's world. The growth study in 2026 rewrote the story of how T-Rex became T-Rex. The next discovery, whatever it is, will rewrite something else. That is the nature of paleontology, and it is what makes it beautiful. And we are not studying a closed book. We are reading a manuscript that is still being uncovered page by page, bone by bone, and every new page reveals something that surprises even the people who have spent their entire careers looking for it. Even after more than a century of study, Tyrannosaurus rex continues to surprise paleontologists. Holly Woodward said that in 2026, and it has been true for every decade before her, and it will almost certainly be true for every decade that follows, we are not finished with this animal. We are not even close. And perhaps that is the thought to carry with you as the night settles in and your mind begins to slow. Somewhere in Montana, right now, in a cliff face exposed by a spring storm or a riverbank undercut by snowmelt, there is a bone. It has been there for 66 million years. It was part of a living animal once, an animal that breathed and moved and watched the world through eyes that saw more clearly than yours ever will. Rain has washed over it for ages beyond counting. Ice has formed around it and melted and formed again. The sediment above it has compressed and eroded and compressed again, and through all of that slow, patient geological breathing, the bone has remained. Nobody has found it yet. Nobody knows it is there. It might be the most complete T-Rex ever discovered, a skeleton that would rewrite textbooks and fill a museum hall and answer questions that we don't even know to ask yet. Or it might be a single vertebra, one bone among billions, telling a small story about one animal that lived and died in a world we can only imagine. Either way, it is waiting. Close your eyes now, if you haven't already. Let the last images of that ancient world dissolve into the darkness behind your eyelids, the warm air, the dense ferns, the flowering magnolias, the distant sound of something enormous moving through the forest with a patience that comes from knowing that you are the most formidable thing alive. Think about the night falling over the Hell Creek floodplain 68 million years ago, the last light fading behind the young Rocky Mountains to the west, the sky above the distant western interior seaway darkening to the east, the pterosaurs folding their enormous wings and settling onto the branches of the tallest conifers, the herds of triceratops drawing together, their horned heads turned outward, the calves pressed close to the adults, the whole herd settling into the stillness of evening. Somewhere in the gathering dark, a T-Rex is lowering itself to the ground. Not the raging monster of the movies, not the screaming, thrashing, perpetually furious creature of 1,000 film posters. A real animal, at the end of a real day, his body radiating the warmth it has absorbed from the sun, its muscles heavy with the fatigue of a long hunt, its extraordinary eyes adjusting to the fading light with a precision that would put any night vision scope to shame. It settles, its breath slows, the great ribcage rises and falls, each breath a little shallower than the last. The sounds of the forest fill in around it, the chirp of insects, the rustle of small mammals emerging from their burrows, now that the giants have gone still, the distant call of something across the river answered by something closer, and the stars come out, the same stars that shine above you tonight, give or take a few billion years of stellar drift. The same moon, a little closer to the earth then than it is now, pulling the same tides, casting the same pale light across a world that has no idea what is coming, that has no way of knowing that in a few million years a rock from space will end everything, that has no concept of endings at all. The T-Rex sleeps. Its brain, that purpose-built sensory processor, dims toward rest. The olfactory centers that can detect blood on the wind fall quiet. The visual cortex that can resolve detail at 6 kilometers goes dark. The neural pathways that coordinate the most powerful bite in terrestrial history relax their constant readiness. For a few hours, The most dangerous land animal the world has ever produced is simply a warm body on a warm night, breathing slowly, still, at peace. Sleep came to T-Rex the same way it comes to you, slowly at first and then all at once. The world doesn't stop because you close your eyes. It just continues without you for a while, turning on its axis. The stars wheeling overhead, the deep patient processes of geology and evolution and time grinding on in the darkness, indifferent to who is watching and who is not. 68 million years ago, an animal closed its eyes on a Cretaceous night, and the world continued. Tonight you are doing the same thing. Different body, different era, same stars, same moon, same slow surrender to the darkness. Nothing about T-Rex was normal. Not its eyes, not its nose, not its bite, not its arms, not the way it grew, and not the world it lived in. Not the number of them that existed, not the way they vanished, not the way they keep surprising us even now, even after a century of looking. There is a particular quality to deep time that is hard to hold in the mind but worth trying to grasp, especially now, as the night deepens and the busy machinery of the day begins to slow. 68 million years. That is the distance between T-Rex and you. Try, just for a moment, to feel the weight of that number, not as an abstraction, not as a figure on a page, but as lived time. If you could somehow watch a film of Earth's history, compressed so that every second of film represented 1 year, the entire span from T-Rex's extinction to this moment would take more than 2 years of continuous viewing. 2 years of watching mountains rise and erode and rise again, of watching continents drift into new configurations, of watching ice sheets advance and retreat dozens of times, of watching mammals evolve from shrew-sized forest dwellers into whales and elephants, and eventually into a species that builds telescopes and writes music and wonders about what came before. Every human civilization, every empire, every war, every work of art, every scientific discovery, every language ever spoken, all of it fits into the last fraction of a second of that 2-year film. All of recorded human history is a blip so small it wouldn't register on the timeline. And yet in that blip, we managed to find the bones of an animal that lived at the beginning of the film and reconstruct its vision and its smell and its bite force and its growth rate and the size of its population. That is an astonishing achievement. It is also a reminder of how small we are and how brief against the backdrop of the planet's actual history. T-Rex lived for 2.5 million years. Our entire species, every human being who has ever existed, fits into about 300,000 years. If T-Rex could have known that, could have grasped the comparison, it might have found us somewhat unimpressive. But T-Rex couldn't know that. It couldn't know anything about us, or about the asteroid, or about the 66 million years that would separate its last breath from our first thought. It simply lived. It woke each morning and perceived the world through senses more acute than ours, and moved through an ecosystem more complex than we will ever fully understand, and it did what all living things do. It survived, for as long as it could, in whatever way it could, and then it stopped. And there is no drama in that, no narrative arc, no moral lesson. Just the quiet persistence of life doing what life does, generation after generation, for spans of time that dwarf everything we consider permanent. And somewhere in Montana, in a cliff face that no one has visited, in rock that has been waiting for 66 million years, the next discovery is already there, waiting, the way the night waits, the way sleep waits. Let it come. Good night. And if you dream tonight, dream of warm Cretaceous air and the sound of something ancient breathing in the dark. Dream of a world that lasted 165 million years and ended in an afternoon. Dream of an animal that could see further than an eagle and smell as well as a cat and bite through solid bone and took 40 years to become what it was meant to be. Dream of 2.5 billion lives, each one complete, each one unique. Each one lived fully in a world that asked nothing of its inhabitants except that they survive and reproduce and leave behind, if they were very lucky, a single bone in a single rock, in a single cliff, face that someone 66 million years later, might find. The night is patient. It has waited 66 million years for you, and it will wait a little longer. Sleep now. The Tyrannosaur is already sleeping somewhere deep in the rock, in the stone memory of a world that was more beautiful and more terrible and more real than any story we could tell about it. The stars turn, the earth turns, and the silence, the deep Cretaceous silence that falls when the apex predator closes its eyes, settles over everything. Rest.